All right, today on The Explainer, we're diving into what feels like a real scientific detective story. It all comes from a 1996 dissertation by Lou Fei. And the mission? To figure out how you can possibly map something so incredibly small, it really shouldn't even be visible. We're talking about the damage left behind by a single, tiny atom. So let's just frame the problem here. Imagine you've got a bullet, but it's the size of a single atom. You fire it at a perfectly smooth surface. How on earth do you see the crater it leaves behind? I mean, seriously, how? That's the totally mind-bending challenge we're going to dig into. Yeah, calling this an impossible target is not an exaggeration. You know, in our little detective story here, the clue we're looking for, it isn't just small, it's basically invisible. We're talking about trying to see damage on a scale that's so tiny, it just pushes the absolute limits of what we can physically measure. And the mission, the actual quest here, was incredibly specific. The goal was to see, and I mean directly see, the damage from just one single 50-kilo electron-volt argon ion hitting a surface. So that's just a super energized atom. They wanted to witness the footprint of one microscopic projectile. No small task. So how do you even begin to see something that's unseeable? Well, you're going to need a pretty special tool, right? But the hero of this story, believe it or not, isn't some microscope with a crazy powerful lens. No, it's a microscope that works in a way that's totally counterintuitive. It doesn't see, it feels. Okay, so this amazing tool is called a scanning force microscope, or SFM for short. And the best way to think about it is, well, it's kind of like a record player for atoms. Instead of using light to see, it uses this unbelievably sharp tip, like the tiniest record needle you can imagine, to trace the landscape of a surface. It literally feels every single bump and valley, and then uses that touch data to build a perfect 3D map. It's brilliant. So how does this feeling thing actually work? Well, it's this really cool technique called tapping mode. So first, you've got this super sharp tip on what's basically a tiny diving board, and it starts vibrating up and down like crazy. Then it gets lowered down until it just gently taps the surface of the sample. Now here's the genius part. A laser is pointed at that little diving board, and it measures even the slightest changes in how it's tapping. As that tip moves across the sample, a computer is just tracking every single little twitch and wiggle, and it uses all that data to build this stunningly precise map of the surface. It's a beautiful solution. Okay, so you've got this amazing tool that can feel atoms. Problem solved, right? Well, not so fast. Having a genius piece of tech is one thing, but before the real hunt could even begin, the team had a huge hurdle to get over. They had to be sure their measurements were actually, accurate. And look, in science, this part is absolutely non-negotiable. It's simple, right? If your ruler is wrong, your map is totally useless. The SFM had to be calibrated with just insane precision. We're talking down to the sub-nanometer level. If they didn't get this right, they could just be chasing ghosts in the machine. I mean, just look at the difference here. An uncalibrated view, it's like you're looking into a funhouse mirror. Everything's warped, distances mean nothing, it's a mess. But a calibrated view, that's the good stuff. That's a true, accurate picture of reality, where every single nanometer is exactly where it's supposed to be. All right, so the ruler's fixed, we trust our measurements. But then another problem pops up. Turns out, every super sensitive instrument like this has its own background hum, right? Its own electronic static. So the big question became, how could they be sure what they were seeing was the actual crater and not just, noise from the machine? And their solution to this was just remarkable. Instead of trying to ignore the noise, they decided to study it, to understand it completely. Now, the dissertation gets super specific, and I'm going to read this directly. A 1 over F alpha law, with alpha equals 0.895 plus or minus 0.008, was found for the time domain noise. Yeah, I know, that sounds incredibly technical, and, well, it is. But here's what that really means in simple terms. They basically took a fingerprint of the machine's own background static. They profiled it, they learned its every quirk. And by understanding the exact signature of that noise, they could just digitally subtract it from their data. That way, they could be confident that whatever was left over was the real signal, the actual crater they were hunting for. So clever. Okay, so let's recap. The stage is set. The microscope, it's calibrated. The noise, it's been fingerprinted and filtered out. It was finally time for the main event, time to fire the atomic bullets and see what they actually left behind. And the experiment itself was really just beautiful in its simplicity. Step 1. They took a sheet of this mineral called muscovite mica and made it perfectly atomically smooth. Step 2. They blasted that surface with those 50 keV argon ions. And finally, step 3. They brought in their finely tuned SFM to scan the impact zone and hopefully reveal its secrets. So what did they find? This is it. This is the moment of discovery. The SFM's map revealed these tiny little pits, only about 10 nanometers across and just a nanometer deep. But wait, there's more. That wasn't all they found. Around each of these little pits, there was a raised rim, about 20 nanometers in diameter and less than a single nanometer high. Incredible! So what does this tell us? It means those little atom-sized bullets didn't just punch a clean hole. Nope. The impact was way more complex. It actually displaced material, creating this very specific structure, a tiny pit surrounded by a tiny raised rim. It was like a perfect microscopic splash, completely frozen in time. So, what's the big takeaway from all this incredible detective work? Well, first, it proved that a scanning force microscope can absolutely 100% image the damage from a single ion, as long as you do your homework with calibration and noise analysis. Second, it showed us that the damage isn't just some simple hole, it's this complex pit and rim structure. And maybe most importantly, this opened up a whole new way of doing science. It proved we could study the entry point of nuclear tracks directly without having to use a bunch of messy chemicals to make them visible. That's a huge deal. I mean, just think about that for a second. This work, all the way back in 1996, proved we could literally map the invisible footprint of a single atom. It really makes you wonder, doesn't it? Now that we know how to see these tiny, tiny impacts, what other invisible worlds are out there just waiting for us to explore?